With the help of this small capacitor, we can convert a single-phase supply into a fake three-phase supply, through which we will test this circuit board. This is the indoor circuit board, and this is the outdoor unit's circuit board. This circuit board operates on a three-phase supply, and its compressor also runs only on a three-phase supply. If the three-phase supply is not present, the compressor will not function properly. Even if one phase is missing, both the circuit board and the compressor will fail to operate correctly. The model number of the indoor circuit board is written here. Similarly, the outdoor circuit board also has its model number written here, which you are able to see. Now, let me show you what the problem is in this circuit. I am now turning on the indoor unit and supplying power to it. As soon as I turn it on, the display shows a temperature of 16 degrees Celsius, and at the same time, an F1 error is also appearing on the display. At this moment, I have provided power to the indoor unit only. I have absolutely no idea why the F1 error is appearing. This circuit board belongs to the Coolman air conditioning brand, and it is from a 4-ton air conditioner. It is a Malaysian company, and we have no available information regarding why the F1 error occurs in this model. So, we need to find out what the problem is. When I removed this circuit board from the unit, I noticed that this connector here was not engaging properly. Let me explain to you what normally happens. I'll press this connector and show you. When you press it, it engages like this. When it engages, what happens is that the three-phase supply passes through to this side, and as a result, the compressor starts running. This outdoor circuit board operates with a three-phase supply. If the three-phase supply is not available, it will show an error, and the contactor will not even start. Therefore, we need a three-phase supply for it to function. However, in my workshop, I only have a single-phase supply. So, what can we do to make it work? For this purpose, I will create a fake three-phase supply. Everything I will show you next in this video will be aimed purely at testing the circuit. Apart from that, no kind of load or operational work can be carried out using this setup. Apart from this, if you have any other method, you can create it at your own risk. Everything I will show you next is purely and solely for the purpose of testing this circuit, so that the circuit behaves as if a three-phase supply is attached and the contactor can turn on. Now, to trick the circuit and create a fake three-phase supply, let me tell you what materials we will need. We will need some wires. I have already prepared the wires here. After that, we will need 2 capacitors. The capacitors must be non-polarized, meaning they are not polarity sensitive, and only this type should be used. The capacitors I have selected are 1.6 microfarads rated for 400 AC volts. Their range should be between 1 microfarad and 2.5 microfarads. If you use capacitors outside of this range, problems may occur, so you must keep this in mind. After that, we will need a connector. This is optional. You can use it if you want, or you can simply join the wires together to get the job done. Now, let's begin the preparations. I have wrapped some tape here, so I'll stick it onto the table. One piece is done, and here goes the second piece. Now, I'll place one capacitor on top of the tape, so it stays in place and doesn't move. Similarly, I'll place the second capacitor on the other piece of tape. Both capacitors are now ready. I'll remove the cover of the connector. Here I have 2 wires. This is my main single-phase supply, and using it, I'm going to create a 3-phase supply. First, I'll connect the blue wire to the connector. Then, I'll connect the second wire, leaving one point of the connector free. So now, the line and neutral wires for the single-phase supply are connected. Next, I have taken another wire, and then one more wire in the same way. I have joined these 2 wires together. This gives me one ready connection. Actually, I also need to add a third wire to this connection, so I'll bring that as well. Now, I will join all 3 wires together and connect them to the live wire through the connector. I have inserted the wire into the connector and tightened it. The first connection we made for the neutral, I will now attach this wire to the neutral terminal. At this point, some of the connections have been completed. When we look at the outdoor PCB, you can see that we need to provide connections for line 1, line 2, line 3, and neutral. Now, what we have to do is connect the neutral wire we previously prepared directly to the neutral terminal. Next, we have 2 wires ready. I will connect these to the phase terminals. You can connect either wire to any phase point. It doesn't matter which goes where. I will connect the yellow wire to line 1 and the red wire to line 2. These 2 connections are now complete. Now, we need to make the connection for line 3. You might remember that along with the main single-phase line, we had created 3 connections, 2 red wires and 1 purple wire. Now, we will take the purple wire and connect it to line 3, This connection is very important because it acts as the main supply that powers the outdoor circuit board. It's crucial that you do not mix up these connections. The phase we are connecting now, L3, is the actual main operating supply for the PCB. We must provide it directly from the main single-phase supply, without involving any capacitors. As I explained earlier, the L3 line is the primary input that powers the outdoor PCB. It must be connected directly to the incoming single-phase supply. Meanwhile, the other two supplies, L1 and L2, are fake phases that we are creating using capacitors. These fake phases must not be connected to L3. Now, we have two connections remaining here, L1 and L2, which are the yellow and red wires. We also have the 2 points that are connected to the single-phase supply. Now, from the main single-phase supply, we will take one wire. We will connect this wire to either side of the first capacitor. We have already prepared the proper system for this. So, I will connect it to the right side connector of the capacitor. The second remaining wire from the single-phase supply will also be connected to the right side connector of the second capacitor. Now, the wires we previously connected to the outdoor PCB terminal need to be connected as well. At this stage, phase polarity is not important. We only need a phase signal. So, you can connect any of the 2 wires to either capacitor. I will connect the red wire to this capacitor here. We are only using this setup for phase detection purposes, so the red wire has been connected. Now, we will connect the yellow wire to the other connector of the second capacitor. With this, our fake 3-phase supply is now ready. Now, I will properly show you how this sequence is working. Now you can see that the connections for line 1, line 2, line 3, and neutral have been given. All 3 supplies are entering directly into the connector. These 3 wires are again coming into the connector where the phase detection circuit is installed. A small mistake happened. I should have shown the testing first and explained the connections afterward. But since I have already completed the connections, we will now proceed with testing to check whether the phases are actually present or not. For this, we will first remove all the line connections, leaving only the neutral connection in place. The supply that we were providing to the circuit board will also be disconnected. The wires coming from the capacitors will be reattached temporarily, but the wire that was carrying the main supply from the capacitor to the circuit board will be disconnected. One red wire, which is from the main supply, and one yellow wire, which was connected through a capacitor, will both be disconnected. In the second capacitor as well, there are 2 red wires. The wire that is receiving the phase, live power, will remain connected, but the wire going toward the circuit board, output, will be disconnected. In this way, we have removed all the phase wires from L1, L2, and L3. Now we will directly perform testing on the capacitors to check whether the fake 3-phase supply is being properly created or not. Now, I will turn on the single-phase power. I have switched on the power. I will set the multimeter to AC voltage mode. We will place the black, negative, probe on the neutral terminal and the red, positive, probe on the phase terminal. Let's check the voltages and see if a phase is being created or not. We are getting 229 volts AC here. Now, let's check the second phase. We will check it on the first capacitor. Keep the black probe on the neutral as it is, and place the red probe on the output terminal of the first capacitor. Here also, we are getting 229 volts AC. So, this confirms our second phase. Similarly, let's check the next capacitor. Here too, we are getting 229 volts AC. This means all 3 phases are properly working. Now, I will switch off the power. We will discharge both capacitors. If there is any stored charge in them, it will be released. We will also discharge the second capacitor. Now, there is no charge remaining in either of the capacitors. The work that I have done afterward. If you are performing this procedure yourself, you should first do the voltage testing before proceeding further. Also, you must confirm on the capacitors that the same voltage you are receiving from the single-phase supply is appearing at the capacitor outputs as well. If the same voltage is not appearing, it means the capacitor you are using might be faulty, and you should replace it. Only after confirming this should you proceed with phase testing or PCB testing. Now, I will reconnect everything exactly the same way I showed you earlier, and after that, I will power on the PCB. Before supplying power, here I have the wire for the indoor PCB. We will also connect it so that the indoor unit can receive the supply as well through the same main single-phase power source we prepared. At this point, all the connections are properly set up. The indoor unit is now properly attached to the outdoor unit. Now I will turn the system on. I have connected all the necessary wires, including the capacitor connections, to ensure proper phase detection. Now I am switching on the power. As soon as I switched it on, all 3 LEDs turned on for a moment and then turned off. Now the third LED has started working. However, the display is still showing the F1 error. Now, next we will see how this 4-ton AC system has been designed. By understanding this, it will become easier for us to fix the current fault and also help us repair any future faults that may occur. For this purpose, I have studied the system properly, and after completing my study, I am now sharing all this information with you. This 4-ton AC is a normal non-inverter air conditioner. It operates using a 3-phase power supply, as I have already explained to you earlier. There is one circuit board in the indoor unit and another circuit board in the outdoor unit. Both boards have separate responsibilities, and I will explain that to you. The indoor unit does not directly communicate with the outdoor unit in any way. What happens is that the outdoor unit sends a signal that the indoor circuit board receives. How that signal is received, we will discuss that a little later. But for now, let me show you where it is received. Here, you can see the optocoupler installed. If I am not mistaken, its marking is either Q1 or 01. You can also see the rest of the system here. This blue wire that is connected here, this is where the signal from the outdoor unit comes in. Now, under what condition this signal comes, I will also explain that to you. You can see here it is marked with a double N, and it is on this terminal that the signal arrives. This signal sent from the outdoor unit is what prompts the indoor PCB to begin its operation. Now, let me explain in detail why this signal is sent to the indoor board. The signal coming from the outdoor unit simply informs the indoor PCB that both of the control systems on the outdoor PCB are working properly. If those systems are functioning correctly, then the indoor unit will allow the outdoor unit to start and begin its operations. The outdoor circuit board includes a complete microcontroller system and several other components. However, the entire setup on this board is only controlling 2 functions. For one of these functions, there is already a connector installed for the 3-phase supply. We need to provide power through this connector, because the entire circuit is designed specifically for phase detection. If all the required phases are present, only then will the circuit proceed to function and send a signal to the indoor PCB. If that signal is not sent, the outdoor unit will also not operate. Whether it's the phase detection signal or this control signal, you can see this white wire here. I have currently connected it in series, or you could say I've shorted it, so that I can proceed with the testing. This is because the high-pressure switch is not currently available in my setup. The high-pressure switch normally provides continuity, and when the pressure in the condenser rises too high, the switch turns off. When it turns off, the 2 wires disconnect from each other, and there will be no continuity. But as long as there is continuity, that means the outdoor unit is working properly, and there is no fault. In that case, the circuit will proceed to operate normally. Now, let me show you how both terminals of the high-pressure switch are working. The main neutral supply comes to N7. Now, if you look here, you can see N6, N5, N4, N3, N2, and N1. All of these are connected together. From here onward, the neutral continues into the phase detection circuit. Now, these 2 wires, one is connected to N1 and the other to common. The neutral comes to this common point, and alongside it, you can see it is marked SIG signal. A relay is installed here, which is responsible for switching this signal. Now, what happens is, between these 2 points, the high-pressure switch maintains continuity. The neutral from N1 reaches this common point. When the neutral stands at the common point and we supply power to the outdoor unit, then if the phases are correct and the system is operating properly, this relay RY1 switches internally and makes a connection. When the relay switches, the neutral is shifted from the common point to the signal point. This shifted neutral signal then travels through the wires and enters the connector. From there, it passes through the blue wire into another blue wire that is connected to the double N terminal. In this way, the signal loop is completed. Now that we've understood how the system works, let's move on to the fault. But before explaining the fault, I want to clarify the remaining functions of this circuit board. This way, in the future, if a similar circuit board comes to me, to you, or to someone watching this video who is working in the field, it will be easier for them to understand and troubleshoot. Here you can see these 2 wires. One is orange, and the other is black. These 2 wires are controlled by relays. The black wire is used to power both fans, which run simultaneously. Once the system detects that the cooling process is complete, it turns both fans off. Then comes the orange wire, which is connected to a heater, either inside or mounted on the compressor. This heater is used in rare situations, such as when excess liquid has entered the compressor. The heater helps to evaporate that liquid, so the system can convert it back into gas and resume normal operation. All of these relays are controlled by the microcontroller on the circuit board. Next, let's look at this connector. The brown wire here is connected to the compressor. The compressor is operated directly by the indoor unit. The outdoor unit does not have control over it. The outdoor unit only performs the two tasks I already explained earlier: sensing the presence of the three-phase signals, activating the signal relay after phase detection. This confirms whether the pressure switch is functioning properly or if there's any issue. Once these tasks are complete, the outdoor circuit's job is done. All other control functions are handled by the indoor unit. Similarly, the purple wire is connected to the heat and cool, reversing, valve, also known as the four-way valve. This valve is activated and deactivated through this wire, allowing the system to switch between heating and cooling modes. In addition to this, the indoor unit manages several other control functions, including sensors. There are two main sensors inside the indoor unit: one for room temperature, one for the pipe coil temperature. These are standard in most air conditioners and are used by the indoor unit to control the system's operation. An additional feature in this system is that the outdoor sensors are also connected to the indoor PCB, not to the outdoor board. You can see here the connector labeled CN8DL, and the three wires connected to it are used for these sensors. This system includes two sensors. One is installed on the condenser pipe, and the other is placed on the discharge pipe. The third wire is for the low-pressure switch. All three of these functions are controlled by the indoor unit. That's why the outdoor unit sends a signal, which reaches the optocoupler. Once the signal arrives, the optocoupler is activated, allowing the 5 volts that are standing across pins 3 and 4 to connect internally. So when the signal reaches this point, the optocoupler gets triggered, and by being activated, it informs the microcontroller that there is no fault in the outdoor unit. This confirmation allows the indoor unit to proceed and control all remaining functions as needed. So the question now is, what exactly is causing the F1 error? As I explained to you, if there is a problem with the high-pressure switch, we can face a similar issue. In the outdoor unit, the F1 error depends on 3 types of faults. The first fault is that if, for any reason, the outdoor PCB is not functioning at all, the indoor unit will still display the F1 error because the required signal will not be generated, leading to this issue. The second fault occurs if there is a phase detection problem, meaning if any one of the phases is missing, then the circuit will again trigger the F1 error because the rest of the system functions will not operate, and as a result, the F1 code will appear. The third fault is that if, for any reason, the high-pressure switch shuts off or stops working, it will cause the neutral connection to be missing at the indoor unit. When the indoor unit does not receive neutral, the optocoupler will not activate, and this will again cause the F1 error to be displayed. These are the 3 reasons that can cause an F1 error. Now I will show you which fault is occurring in this PCB. The phase detection circuit is working perfectly fine. There is no issue with it because the 3-phase supply that I generated is functioning correctly. I also checked the high-pressure switch on site, and it showed continuity, so it is confirmed to be working properly. Now, the real problem is that the signal from the outdoor unit is not reaching the indoor unit, which is why this issue is happening. We will now try to find out why the signal is not coming through. Now all the required components between the indoor and outdoor units are complete, and the fake 3-phase supply has been generated. So let's now see what fault this PCB is creating. I am now connecting the power supply. I turned on the switch, and the unit powered up. The relay has also switched. When the RY1 relay switches, it means that the phases and the pressure switch are working perfectly fine. These are the only 2 controls managed by this PCB. After that, the PCB's next task is to activate the RY1 relay. As soon as it switches on, the signal will be sent toward the indoor unit. When the indoor unit receives this signal, it will detect that there is no fault in the outdoor unit, and it will proceed to turn on the compressor. Now, my personal assumption is that the signal is not reaching the indoor unit, which is causing this problem. To verify this, we will use a multimeter. Since the relay is switching properly, and from the signal point, the neutral should be coming after the relay switches, we will now check why the signal is not reaching the indoor unit. So let's check it now. I placed one multimeter probe on the signal point and the other probe on either side of this resistor. As you can see, it is showing 0 volts here. Now let's check the other side of the resistor. Again, there are no volts appearing. This means that our neutral is not functioning at all. Now what we will do, since the neutral signal is not reaching up to this point, so we will move to the common point. I will place one multimeter probe on the common and the other probe on this resistor to check. As you can see, we are getting 90 volts here. Now if we check further ahead, we are still getting 90 volts. Now let's check the voltages at R2. Here as well, we are getting 93 volts. When we follow the circuit step by step, we come to a diode D1. Let's check the anode side of D1, while keeping the neutral at the outdoor unit's common point. As you can see, we are getting 233 volts here, which means this part is working fine. Now, checking the other side of the diode, we get 166 volts. Similarly, when we check at our 201, we are getting 164 volts there as well. This means that when we check from the common point, the signal is properly present and everything is working fine. However, when we check directly at the signal wire, there is no voltage, meaning the neutral is not reaching there, and this is the fault. The problem lies in the RY1 relay. The relay has developed a fault. Its internal contact points have built up carbon deposits or some damage, due to which they are not connecting properly. As a result, the signal, or the neutral, is not being transferred from the common to the signal wire. This is causing the issue. Now, we will replace this relay and check whether this was indeed the root cause of the problem. Now I have removed the faulty relay, and we will install a new relay in its place. After removing the relay from the system, we will first check whether it is actually faulty or still working properly before proceeding further. So, let's test it now. Here is the relay. It is a 12-volt operated relay, and it can work with either AC or DC voltage. Now, I will supply 12 volts to its 2 coil points, connecting the positive and negative accordingly, and I will place a microphone close to it so that we can hear the clicking sound when it operates. I have set the multimeter to continuity mode, and will check the relay through the meter. First, I checked it without supplying voltage, and it shows disconnected. No continuity. Now, as soon as I turn on the supply, we can continuously hear the continuity beep sound. If I turn off the supply again, the beeping stops. When I turn it on again, the continuity sound immediately starts again. This means the relay is operating properly and switching correctly. After testing the relay, we found that it is working perfectly fine and there is no problem with it. Now we will perform another test, a simple but highly effective test, which will give us a better idea of where exactly the problem lies. For this test, we will take a wire and use it to perform the check. Here we have the main neutral wire from the single-phase supply that we already connected, and now we will attach this additional wire to it. All the other connections are already in place, so we will connect this extra wire alongside them, and it is now ready. What I will do next is disconnect the signal wire from the indoor unit so that we can perform this test properly. I have now removed the signal wire. You need to observe this test carefully because it will give us a lot of clarity on what we need to do next. If the relay is confirmed to be fine, then we need to find out what other fault could be present at this point. Now, what we have done is connected the wire, but the power supply has not yet been turned on. You must carefully observe the screen now. I turned on the system, and it showed 16 degrees, but immediately after that, the F1 error started appearing. Now, how can we eliminate this F1 error? We will check it using the wire we prepared earlier. Remember, this wire was connected to the neutral. Now we will attach this wire to the signal wire, and you will see that the display shows 16 degrees, and one of the relays has also switched. In this way, our system is working perfectly fine. Also, notice that as soon as I removed the wire, the F1 error started showing again. This confirms that our indoor unit and its signal circuit are completely fine. The only issue is with the signal itself. There is no other problem at the indoor side. Now, our full focus will shift to the outdoor circuit because the fault lies there. We will continue checking to find out what exact issue in the outdoor unit is causing this problem. For now, we will turn off the system. Now, we will test the outdoor PCB to find out what problem is causing this issue. For this, we will once again supply power to the system, and as soon as the electricity is supplied, we will begin testing. As you can see, I have already removed the relay, and we will now measure the voltage at the points where we expect to find around 12 to 14 volts. Let me explain how we will do it. We will connect the two probes of the multimeter, the positive probe to the positive side, and the negative probe to the negative side. This test will give us a good idea of what's happening. It is important to hold the probes properly before starting the system, because if we try to place them afterward, we might miss what actually occurs. So I am holding both probes in place, and now I will turn on the electricity. Keep a close watch on the multimeter. As soon as I powered on the system, the meter showed 16.7 volts for a moment, and then the voltage dropped down to 0.372 volts. What's happening here is that the relay switches on once, and then immediately switches off. We can hear the clicking sound when the relay switches on, but when it switches off, there is no sound, which makes it harder to detect. So after the relay turns on, it unexpectedly shuts off again, and this seems to be the main problem. Now, let's check the circuit further to find out exactly why this is happening. Now, if we look at this circuit, here we have a 5-volt regulator, and this is a transformer-based circuit. This means that 220 volts are supplied at these 2 points, and from there, we receive 12 volts. Here, an AC bridge rectifier is used, which converts the AC voltage into DC voltage. The DC voltage then passes through a capacitor, and we get around 15 to 16 volts. This voltage regulator then steps it down to 5 volts to power the microcontroller. The 15 to 16 volts are also supplied to the relay, which enables it to turn on. To trigger the relay, there is a 10 kilo ohm resistor connected here. You can see that pin 27 of the microcontroller is linked to this point through this resistor, and after passing through it, there is a simple diode marked BHD. From there, the circuit goes through a 0 ohm resistor and connects to a neutral point. On the positive side, you can see there is a capacitor, part of the SMPS, and from there, the connection goes directly to the positive point of the relay. So basically, the relay's positive side is being powered directly, and the negative side is controlled by the microcontroller. Now, we will also check these signals to see exactly what is happening at this stage. For this, we will first prepare everything properly. We will connect the positive probe of the multimeter to the positive point, and then, because the signal should come from the microcontroller to this point, we will place the second probe there. Now, I will turn on the system, and you need to watch carefully. When I turn the system on, the voltage at the diode side showed 16.91 volts. However, when I checked on the other side of the diode, connecting the positive probe again, there were no volts appearing there, while on the back side of the diode, it showed 16.94 volts. This indicates that either the diode has gone faulty, or there could be some other related issue as well. As I explained earlier, this circuit controls only 2 main functions. The first main function is to detect the signal, which allows the system to confirm whether all 3 phases are properly present or not. If even one phase is missing when the unit turns on, there is a high risk that the compressor could get damaged. To prevent this, this detection circuit has been added. The second function of this circuit is to activate the relay and send a signal to confirm that there is no high-pressure issue and that the system can operate smoothly. Now here we can clearly see and feel that there is a problem, so for now, I will turn off the system. Now for the 3-phase detection, this circuit is present. Here you can see the diodes at positions 12, 11, and 10, along with resistors R203, R202, and R201, and some capacitors. On the other side, a few optocouplers are installed, which help the system detect whether the voltage is proper or not. I will now set the multimeter to resistance mode and check all the resistors and diodes one by one. First, let's check the diodes. When I checked them, all 3 diodes showed to be perfectly fine. Next, I checked the resistors, starting with the 100 kilo ohm resistors. R201 showed 100 kilo ohms correctly. R202 also showed 100 kilo ohms. R203 also checked out fine. Next, I moved on to the smaller resistors, R20, R19, and R18. First, I checked R20, which should have been 10 kilo ohms, but it showed only around 250 ohms, which is much lower than expected. Then, I checked R19, which showed 9.80 kilo ohms, and R18, which showed 9.88 kilo ohms, both of which are correct. Now, because R20 is not showing the correct value inside the circuit, and although sometimes readings can slightly differ inside the board, this much difference indicates that something is definitely wrong with this resistor. Therefore, it would be best to remove R20 from the board and test it separately to get a clearer and more accurate result. I have now replaced both components, the capacitor and the resistor, since the issue was occurring in this section of the circuit. I installed a new resistor first, and for the capacitor, I selected one with a slightly higher voltage rating, but it's still the same value, 104, 100 nanofarads. So I've installed both, and now the circuit is functioning properly. Let me explain exactly what I've done, and also tell you what the remaining possibilities were, which we can now rule out. So first, the resistor labeled R20 was not showing the correct value earlier, which is why I replaced it. Let me now show you the new value. I'll set the multimeter to ohms mode and check it. As you can see, it's now showing a perfect 10 kilo ohms. I also replaced the diode connected alongside it, as well as the capacitor. The reason I replaced these components was that the required voltage wasn't being generated, the same voltage needed to activate the optocoupler. I'll also show you shortly that the correct voltage is now present, and finally, I'll explain exactly what the fault was and why it was happening. Now I've turned the power back onto the system. The system has started, and the relay has switched on, but then it turned off again. Let me explain the reason behind that as well. If we check pins 1 and 2 of the optocoupler and measure the DC voltage there, we see it's about 0.570 volts, which is roughly half a volt. Because of this, the optocoupler is activating. And now let's check the voltage from emitter to collector. Using the capacitor's positive terminal, I checked the emitter pin, which is showing 5 volts. When checking the collector pin, it shows 2.3 volts. This indicates that the system is working correctly. However, the problem lies in the 3-phase simulation. It's not functioning properly. That's because we only generated voltage phases, but not their proper frequency and 120-degree phase difference, which is essential in true 3-phase systems. In a proper 3-phase supply, there is a 120-degree difference between each phase. This means one phase turns on and off with a 6.6 millisecond delay, and the difference between the first and third phases is 13.2 milliseconds. This time difference is essential. The setup we've made here uses just a single-phase simulated system, so it doesn't produce the correct phase shift, and because of this, the system continues to show an error. Still, I have resolved the previously existing issues, and I'll show you exactly what those issues were. After that, I will also demonstrate how to test all the optocouplers to check whether they are working or not. If even one of them is faulty, we'll be able to identify it here, but proper real-world testing must be done on an actual 3-phase supply. The fake 3-phase setup I've created is only effective when basic phase presence needs to be detected. However, this system is quite smart, as it not only detects the presence of phases, but also checks for the 120-degree phase difference. If that difference is missing, it treats it as a fault and continues to show an error. The system I've built is designed only for specific tasks. It cannot be used for everything. I mentioned this at the start of the video, and I'm repeating it now. This setup is only suitable for limited purposes. For example, in the work I just demonstrated, frequency and phase angle difference are both required. Otherwise, this system will continue to show errors. I've now turned the system off, and I'll explain what exactly I changed in the circuit. As I told you, I replaced the optocoupler, and I'll now explain why I did that so it's clear. Here's the optocoupler I removed. Let's look at pins 1 and 2, which are for the emitting diode. I checked it in diode mode, and it showed a voltage drop of 0.336 V. Then I reversed the probes, and it still showed 0.363 V, which indicates that the internal diode had short-circuited. That's why the optocoupler was faulty and needed replacement. Now let me show you how to test all 3 optocouplers, even without a real 3-phase supply, to confirm whether the system is functioning properly. For this, take 3 wires, representing L1, L2, and L3, and connect them all to a single-phase line. This means all 3 phases are now receiving the same signal. I've also connected the main power wire and routed all 3-phase wires to the outdoor circuit. On the circuit board, I've connected them to the 3-phase connector line by line. Now I'll turn the board over, remove the connector from the board, and plug the 3-phase wires into it properly. At this point, the system is getting power on all 3 phases, but since it's from a single-phase line, all 3 are working on the same frequency with number 120-degree difference between them. As a result, the system detects that the required 6.6 millisecond phase shift is missing, which is why the orange error light turns on. Next, I'll show you how to confirm that everything else in the circuit is working. We'll test the output of all 3 optocouplers. Using the positive probe on the capacitor's positive side and checking the optocoupler outputs with the negative probe, we see 2.3 volts on the first one, the same on the second, and 2.38 volts on the third. This confirms that all optocoupler outputs are functioning properly. The only issue remaining is the missing 120-degree phase shift. Everything else in the circuit is working correctly. The final check is to confirm whether the green status LED turns on. If it does, the system will operate normally. With this, our circuit testing and setup is complete. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.